Hello, everyone. My name is Manny Young, and I would like to welcome you all to PyData Global 2021. Today, we have a speaker here. His name is Eric Ma, and he'll be talking about an attempt to demystify graph deep learning. Eric is a principal data scientist at Moderna, and actually, yeah, I think that is just where I would just try and stop so that he just goes straight into his call because the bio is a little bit lengthy. Please, if you have any question, you can make use of the Q&A session, and I think I'll just hand it over to you, Eric.
Okay, thank you very much, Manny. So hi, everybody. I'm Eric. Like 4 years ago at PyData, I would like to do an attempt at demystifying graph deep learning. So yeah, like I said, 4 years ago, I did a talk at PyData in NYC, and I tried to demystify Bayesian deep learning. And 4 years later, here I am trying to demystify graph deep learning. For those of you who want to follow along on the slides at your own pace, I've actually put the slides in the chat, so please feel free to go ahead. Oh, sorry, I would like to paste it for everyone. Please feel free to follow along on the slides on your own pace. If you find me boring, I am completely unoffended if you do so. So just to briefly introduce myself a little bit, as Manim said, I currently work as a principal data scientist at Moderna Therapeutics. Yes, this is the Moderna that is one of the two companies that have successfully brought a COVID-19 vaccine onto the market. We're on a mission to make mRNA medicines and leverage the power of mRNA to do some really cool stuff to make therapeutics for people who need them. And the team that I'm on, we're hiring like crazy right now. I'd be happy to talk about jobs and positions and potential opportunities that might be showing up in the near future. Prior to that, I was at the Novartis Institutes for Biomedical Research. Likewise, over there, I did a lot of enzyme engineering, data science work, as well as chem informatics related data science work, mostly in the realm of like machine learning systems. But there were also really cool novel models that I got to explore with colleagues and stuff. And so that was really awesome to see. And prior to that, I was in the Department of Biological Engineering at MIT, where I did my thesis on influenza research. And one of the fun facts is I actually joined Moderna because there was an opportunity to go back into the influenza world, which was my professional history for a good chunk of time. I'm really glad to be back in that world again. I think part of my own mantra at work has been to accelerate science to the speed of thought. That is where my headspace lives professionally, has lived for the past 5 years thus far. And in my toolkit, it's usually deep learning, Bayesian stats, and network science. And I partner up with colleagues who work at the bench, who do imaging work and all sorts of NLP kind of work as well, to really try to accelerate science, make science go as fast as the human can think about new ideas. Okay, so let's get into the motivation for this talk. How many, if you've heard of this guy, Ferenc Huszár, I hope I'm pronouncing his name correct. He's got this tweet from 4 years ago, which basically reflects my sentiment around the world of all of these deep learning explainers and blog posts. It's way too math heavy for my taste. Part of the reason is because after X many years of trying to learn deep learning on my own, I realized that my hack has always been to learn learn the math of deep learning by programming and by drawing pictures and not by staring at equations. So I am out to solve point number 4 in this talk. Where are all the pretty pictures that explain the math behind these complicated concepts? Okay, so this is a talk on graph deep learning, which means that we probably have to take a step back and start by asking what are graphs, right? So let's talk about that. When you think of graphs, I want you to think of networks of all kind that you can see inside your daily lives. We know that there are social networks like Twitter and LinkedIn. We know that there are flight networks between airports. We know that there are transportation networks. There are road networks between cities. Any kind of network that you can think of should be your anchoring example for what graphs are. So what are graphs then? Graphs are actually comprised of 2 collections of things. Graphs are comprised of nodes and edges. Nodes are those red dots that you see on this chart, on this diagram over here, and edges are the yellow lines that you can see over here. So red dots are the nodes. They are entities that you can count, things that you can enumerate, all right? Things that, you know, are not abstract ideas, but actually like real things that you can count, feel, etc. So people in a social network would be one example. Airports in a flight network are another example. And then there are things like the edges, which actually are the relations between these countable things, right? So in a social network, you would connect people based on whether they were professionally acquainted or not, or whether they are friends in real life. In a flight network, you would connect airports according to whether there's a flight path between them or not, all right? So really, when you think of networks, when you think of graphs, I want you to think about networks. Now, herein lies the problem. Everything about deep learning operates on arrays. These guys here, they don't look like arrays. So that begs the question, if we have this thing called graph deep learning, how exactly do we represent graphs as arrays? So that is the first thing that we're going to explore. I'm going to pull out an example from my professional life that I've always gone back to as a minimally complex anchoring example. It's got a bit of chemistry inside there. If you've taken high school chemistry, you'll totally get what we're talking about here. Here's the molecule. It's an organic molecule. Actually, the fact that it's organic is not really important itself, right? The more important thing is that it's got nodes and edges. What are the nodes in this graph? The nodes in this molecular graph are the atoms, and the edges in this molecular graph are the bonds between those atoms, okay? So that's a molecule represented as a graph. Now, here is the exact same molecule with numerical properties annotated on each of the nodes, right? So let's say we decide to go in and annotate every single atom in the graph with the atomic mass and the number of valence electrons that it has. The atomic mass being basically, the atomic number being the number of protons that atom has, and the valence number being the number of electrons that are present in its outer shell of its electron shells. So carbon has 6 protons and 4 electrons in its outer shell. Hydrogen has 1 proton and 1 electron in its outer shell. Oxygen has 8 protons and only 2 possible bonds. I got the definition of valence wrong. It's actually the number of bonds that it can form. So it has 2 possible bonds that it can form as a result of 2 valence electrons. And so this is how you would represent the same molecule with numerical properties. And now what you can do to obtain a complete picture of the numerical properties of all the nodes is take all of these vectors over here and stack them up on the right. Here, the order might matter, and it will matter when you think about the coming operations that are going to show up later on. But for now, take me at my word that in order to obtain the node, what we call the node feature matrix, which is a complete picture of the numerical properties of each of these nodes, you order them, you stack all of these up in a particular order that you get to determine together beforehand, and you get back what we would call a node feature matrix, all right? So we now know how to represent nodes as arrays. And as Jim Sheldon has noted inside the chat, you actually have another way that is a very useful tool for representing the edges as an array. So let's take a look at what we call the adjacency matrix. The adjacency matrix essentially lets us represent edges in a graph. And in this particular adjacency matrix that we're showing over here, it shows ones anywhere that an edge exists between a pair of nodes. And it shows an empty entry everywhere else. Don't worry, Jim, it's all good. I appreciate the engagement. I really, really love that. So adjacency matrix, this particular adjacency matrix is what we would call a binary adjacency matrix. It's 1 if you have an edge and 0 if you don't. Note that this adjacency matrix is actually symmetric because the graph is undirected. Here's an alternative adjacency matrix that you could show, right? This is another adjacency matrix that shows the number of bonds between atoms, all right? So most of these edges are single bonds, but there is one over here between atom number 2 and atom number 6 that has 2 bonds in between them. And so the corresponding entry in the adjacency matrix has the value of 2. Okay, so let's take a step back and summarize this section thus far. We have graphs. We want to be able to put graphs inside a neural net model, so we need the array representation. The array representation of a graph comes in 2 forms, and you actually need both forms together. You need the node feature matrix to represent nodes, and you need the edge adjacency matrix to represent edges. And these 2 together give a complete numerical representation of the graph. So now we need to talk about another pretty elementary math operation called message passing. Message passing on graphs, that's the next thing that we need to explore before we can build our intuition about what graph neural networks are. So I'd like you to focus your attention first to the left-hand side of this figure. Over here, you will see a chain graph. This chain graph has 4 nodes. It starts from node 1 all the way to node 4 over there, okay? I've cloned in this figure the chain graph to represent things that are happening over time. So let's focus our attention on the top left-hand corner first. We might have a message that exists on one of these nodes at a particular moment in time, and that's represented by the blue dot on top of that particular node. Okay, so what we do in the goal of message passing is to take that blue dot and move it along the graph according to where the edges point towards, okay? And if you do that over a number of time steps over here, as we're showing over here, as you go from time step 1 to time step 2, the blue dot will pass from node number 1 to node number 2 based on the arrows that is between node 1 and 2, all right? If you do that again, it goes from 2 to 3, 3 to 4, very intuitive stuff. Let's take a look at the placement of the message on the graph. That actually has an array representation as well, and it looks something like this guy over here. You have a vector that has a 1 where the message is and 0 everywhere else. You also have the adjacency matrix, which, by the way, stays the same all throughout the entire message passing operation. I'm going to put it to you that if you try to simulate this in NumPy on your own, when you do the dot product between this message vector and the directed adjacency matrix that shows up over here, you will be able to accurately simulate the progress of the message from the first node to the second node to the third node to the fourth node, and then finally off into oblivion because there's nowhere to pass the message, using nothing more than linear algebra operations. For those of you who are astute and looking at the matrix multiply on the right and going like, that can't possibly work, you've got to transpose something over there, you are absolutely right. I've structured this vector as a vertical vector, column vector, and not a row vector, simply for convenience and spacing. I don't have enough space to draw a horizontal vector. So please ignore the fact that a transpose is absolutely necessary to make this work. Now, if you if you did a bunch of other transposes and reverse the order of operations, you'd actually get the adjacency matrix dot product the feature matrix, which is the kind of convention that I'll be using the rest of the slides. But this was an illustration that needed enough space on my iPad when I was drawing it. So I'm going to just put this to you that message passing on graphs, again, is nothing more than a dot product of matrices. And that's shown in this like little simple Python function that is on my slides over here. Okay, so let's look at message passing in the context of our minimally complex example to see how message passing works. And for this, I'm going to have you focus on the bottom right-hand corner of this molecule over here, where we have the carbon, oxygen, and hydrogen. Those three atoms will sort of be our focal point for this part. So notice how we have the vector 6, 4, 8, 2, and 1, 1 on these 3 nodes respectively. When we do message passing, the whole idea is we take our neighbors' values and we pass them into ourselves. They get passed into ourselves and we sort of sum them up. That is the most elementary message passing operation that you can do on this particular graph. So the result of that would be you take 6 and you add 1, and that becomes the value 7 over here. You take 4 and you add 1, and that becomes the value 5 in the message passing result. Same goes for this hydrogen, right? This hydrogen has the value 8, takes its value 8 and 2 from its neighboring oxygen, right? And so that after one round of message passing, you get an 8-2 vector on the hydrogen. And then for this carbon, well, it's got summations from this carbon, oxygen, and other oxygen. And trust me, the math works out. You get something that is 22,8 for that vector over there. And I'll put it to you, keep this notation in mind, that this is an adjacency matrix dot product the feature matrix to give you exactly this result. Okay, so now how do we connect message passing neural networks to message passing to neural networks? So let's talk about that. I've decided to move away now from drawing graphs over and over and over because that's going to get really tedious. So we're going to do a bit of abstraction over here. We've got the adjacency matrix and the node feature matrix, and we can define math operations that are basically like Python functions. A message passing operation that accepts an adjacency matrix and a node feature matrix gets you the message passed matrix. Now here's where the neural net stuff happens. You can actually take a feed forward layer that operates on graph, the output of the graph, output of the message passing operation, and return, pass it through and pass it, you can pass that thing, that Z matrix through a feed forward neural net where you have learnable parameters to return neural net transformed version of the message passed matrix, right? And there are learnable params inside here, which means this node level, this is what we would call a node level embedding of our, learned embedding of our original graph. And that is basically the kind of way that you connect message passing with neural nets. It's literally nothing more than this at its core. If you are doing neural net models that operate on predicting a single number per graph, sometimes you might need an operation to summarize all of the graph nodes into a single vector. So you get a graph level vector rather than a per node vector. And so you can do a summation operation which sums across nodes and gives you back a single vector for that graph. Forgot to mention, by the way, summation is not the only operation you can do. You can do a mean, you can do anything else that reduces the dimension by 1, collapses the node dimension, basically. So there is research that is being conducted on basically what operation would be considered, say, mathematically injective, such that you get a one-to-one mapping from graph to the vector that you have that is resultant from there. And so if we're to connect everything together, you would actually get this schematic diagram, right? You start with your graph data on the left-hand side. You can do message passing plus feed forward operations, which give you the result of message passing and some nonlinear transforms inside there. And then you can pass it through, again, a graph summary operation to get a graph level summary vector if you are doing a graph property prediction per se, and then pass that through yet another neural net operation to get the output that you're interested in. And that is graph deep learning demystified. But that's not the end. Let me show you, as a little bit of a bonus, some code, right? Actually, if this is probably better read on your own. Let me see if I can zoom in a little bit. So the code basically looks something like that. You can define a message passing operation that accepts graph data. You can define a graph summary operation that returns that particular thing over there. You can do a graph neural net feed forward operation as well, purely in NumPy code. You can do feed forward operations, define a feed forward operation like that. And if you define a Python model, what you might the code that you might write actually looks something like that. So I'll leave this there for you to browse on your own on the slides, think about it, ponder about it, and sort of get a flavor for what exactly is happening behind the scenes when you're thinking about graph neural net operations. Here is a bonus fact, by the way. If you take convolutions, they actually look a lot like message passing. So let's look at convolutions on images, all right? We start with a pixel grid that looks something like that in blue. And we have a convolutional filter in red that looks something like this. It's got ones on the outside and 0 on the inside. And if you do the convolution operation with certain padding and border settings, then you will get this particular array as a result, okay? So far, so good? All with me so far? If you think about pixels on a grid, pixels are entities and they share a spatial relation with their neighbors, which means they can be represented as a graph, which actually means you can take each of these pixels, represent them as a node on a lattice grid, and draw edges between any pair of nodes that are neighboring to one another. And if you do a simple message passing operation on this grid over here, you will get the exact same result as a convolution with that particular filter. So I put it to you, there's some really, really cool connections between these two ideas, really fun stuff. So when do we use graph neural nets? Well, that actually exposes a deeper question, which is when do we use what types of neural nets? And I really want to start a discussion, maybe even hammer home some points over here. Partly because I've reviewed machine learning papers in which the authors used convolutional neural networks on tabular data, which made 0 sense. It was not principled at all. And I wrote that in the review, and it was very, very surprising that they did that. The only motivation that I could think of for them trying that was the authors were just enamored with neural nets and wanted to have an excuse to try CNNs. So when do we use what types of neural nets? Well, basically looks like this. You have to think about the inductive biases that you're trying to encode in your model. Feed-forward neural nets encode the bias of interactions between features. Convolutional neural nets encode the inductive bias of spatial correlations. Sequential models, which are recurrent and autoregressive models, encode the inductive bias of temporal or sequential dependencies, and graph neural nets encode the bias of relational data, all right? Wherever you have relational information, graph neural nets are an appropriate model. Otherwise, not really. All right, so here's the summary. Graphs can be represented as matrices. You have the node feature matrix as well as the adjacency matrix. You need both of these matrices in order to be able to numerically represent a graph. You can't do without either of them. Also, graph deep learning is essentially anchored on message passing. If you know message passing, you know the basics of graph deep learning. With that, I'm going to leave you with some resources to learn more. You can click on any of these links. There are some really good ones. I particularly like the Gentle Introduction to Graph Neural Networks, which came after my essay. This one's on distill.pub. It's by some friends of mine at Google. Really, really cool stuff. So that's a really good resource to learn even more about this field. And with that, I'd like to thank you for your time, and I'm happy to answer questions.
Thank you very much, Eric, for your talk. I think if you move over to the question session, we'll be able to see 2 questions actually.
Yeah, definitely.
Would you love to take them now? Yeah.
Definitely. So Alexander has 2 questions. I will answer live the first one, the easier one first. So let me go back here. The slides are available up here at this link. One more time, I'm going to copy them into the chat so that everybody has access to it. So send the chat to everyone. All right, so that's the easiest question of them all answered. So then Alexander's second question was, in our example, we showed implicitly a supervised scenario. How about unsupervised learning scenarios, such as using contrastive losses? What are your thoughts? My thoughts are totally doable. If you think about what the structure of a supervised machine learning model is, in classical statistical terms, what you've got is a fancy link function between your input and output, all right? Now, if you think about what you're trying to do in an unsupervised setting, there is actually this really cool connection to probabilistic modeling where you're trying to learn the structure of your data based on some form of likelihood. And inside there, if you're thinking about mixture models, which is, again, my anchoring example for unsupervised learning scenarios, if you can write a likelihood for your mixture model based on your data, you can use GNNs as the fancy link function to give you your likelihood calculation. It literally is that. Happy to talk more offline. I think this one is a big. This one's a fairly big question to go deep into. So happy to talk more later on. But basically, the idea here is just as you know how you can use feed-forward layers and convolutional layers in an unsupervised setting, think of graph neural net layers in exactly the same mold as those guys. And if you really want to broaden the way that you think about these layers, they are fancy link functions like the logistic function, all right? So that's sort of my perspective on this over here. So that's my answer. That question has been answered live. Severin has a question. So GNN, it's just a custom NN architecture, and the answer is yeah, but one that does have a few API design implications, right? Like you notice you're not just accepting one vector of data, you're accepting actually two vectors of data, right? So yeah, that is something that you would probably need to keep in mind if you're designing an API for graph neural nets. And then Lewis has the question, what inductive biases are encoded in non-autoregressive graph transformers? Lewis, I don't wish to butcher the answer to this question. So let's take this offline, partially because I actually don't really know much about non-autoregressive graph transformers. I'm familiar with transformers, I just have not seen the underlying implementation of non-autoregressive graph transformers. So I'd really love to explore that in maybe a different setting. So I'm sorry, I don't want to answer that question at this point, but it's because I don't have enough knowledge to answer it publicly, and I don't want to give you anything incorrect. Okay, and then we have some other questions that are showing up inside the chat. Let me just see here. Can I share my contact info for future questions? My contact info is on my personal website. So if you just go to the base URL of that website, you'll find the contact page over there. And Sarunas has another question, which is probably the last question I'll answer. Well, actually, that one's a bit of a complicated question. I'm going to skip over to Shikalam's question, which is what DL framework are you usually using for graph neural nets? I've actually used JAX and stacks and then implemented custom layers on my own for message passing. But if you don't want to do that, you can actually use JRAF if you're in the JAX land. And I think there's PyTorch geometric if you're inside the PyTorch land. I really like JAX, by the way, even though I don't get to use it at work. JAX has all these wonderful, wonderful ideas on the most idiomatic array API ever. So I definitely like JAX a lot more. Cool. Manny, I think we're at the end of time. Is that correct?
Yes, please. We just wanted to just let you know. And also, please, those of us who have more questions, we can also move that to the Slack group and also to the Gather Town as well. Thank you very much for your talk, Eric. It was actually great listening to the talk. And I also want to thank everyone for taking their time to listen to his talk as well. I think next on the agenda, we'll be having a break. So I'll be stopping the recording now. And thank you, everyone, once again.
Thank you very much, Manny.